welcome to my talk about Shift, an efficient and flexible search engine for transfer learning. To set some background, transfer learning consists of two parts. One is an upstream pre-training phase where a very large dataset is used to train a neural network from scratch. Now, this neural network consists of two parts. First, the feature extractor, which are usually all the layers until the last one, and the linear head at the end. Now, in a second phase, in a downstream process, a user's dataset, which is usually much smaller, is used to fine-tune the same neural network architecture. But instead of randomly initializing the weights, we copy over the weights from the feature extractor. Now, this has two benefits. First, it's cost saving because the downstream dataset can be much smaller. And secondly, it's also time saving because we don't need that many epochs for the neural networks in the fine-tune process to converge. Now, in practice, we usually don't have a single pre-trained neural network, but we have a lot of neural networks models trained upstream based on different data sets. Now, users usually pick one or two out of those and fine-tune them on their own user's dataset. The question is, which model should users use? And there are different search strategies. We categorize them into four different categories. But the goal of all the search strategies is, given a set of models, to create a ranking so that user can select the top one or top two model. Now, the first category are task-agnostic search strategies. These search strategies look at metadata of the models and create a ranking solely based on those. The second category are task-aware search strategies, where the user's downstream dataset is used together with some cheap proxy to create a ranking. The third search strategy category uses a set of benchmark dataset, which all these benchmark dataset can be fine-tuned on all the upstream models in an offline fashion. And now these table of all fine-tuned accuracies can then be used in a meta-learned task-agnostic fashion in order to create a ranking. And the last category uses some similarity between the benchmark datasets and the downstream datasets in order to create a ranking in the meta-learned task-aware fashion. Let us look at two task-aware search strategies because these are widely used in practice. The first task-aware search strategy is linear evaluation, where instead of fine-tuning the whole neural network, we freeze the feature extractor and only train the linear head, making it much cheaper compared to fine-tuning the whole model. And the second one, we can even deploy another, or in this case, cheaper classifier instead of a linear classifier by, for instance, getting the KNN accuracy. Now, if you look at existing online model repositories like TensorFlow Hub, you realize that the only way you can, or the only category of search strategies you can apply are task-agnostic ones, meaning that you can filter model based on their metadata, but you cannot have any use your downstream dataset in a task-aware fashion. So this is the first need for Shift. Existing model hubs only support task-agnostic search strategies. But the second one, which we analyzed in a companion work published last year at CVPR, is that we realized that no search strategy outperforms all the others on any or a large set of possible tasks. But combining search strategies or defining hybrid search strategies are usually a good starting point. So overall, we need a way to flexibly define and run model search queries, and we also want them to be efficiently executed initially, and also because machine learning and data science in general is an iterative process, we want also to have an efficient iterative execution of these queries. So overall, based on these requirements, we built Shift. In Shift, a user defines a query in our own DSL and gets back a list of models. So example queries supported by Shift, which are also proposed by related work, all aim at limit and ordering of restricted models by, for instance, their best reported upstream accuracy, which is a task-agnostic search strategy, or by their best nearest neighbor classifier accuracy, best linear classifier accuracy, which are both task-aware search strategies, or mixing task-agnostic and task-aware. So for instance, this is something we proposed in our work from last year, or finally also meta-learned task agnostic search strategies or task-aware search strategies like task2wek. Let me give you an example of such a hybrid query supported in Shift. In this example, in the first part, we want to get the best model for the vision domain with at most 10 million parameters based on the upstream accuracy. Now we also want to include a second model, which is not the same as the one retrieved by Q1, based on the best linear classifier accuracy. Now, in order to build Shift, we define a logical model for transfer learning. In that, we support different model repositories and also different dataset representations. We create two views. One is a model view, where we represent all the models coming from different model repositories, and one is a data reader view, where we represent datasets, let it be benchmark datasets, but also users downstream datasets in different formats. Then we have two different scoring views. One are dataset similarity views, which take data reader as input, and the others are proxy scoring views, which take a model and the data reader as input. Now, these views are only populated upon demand lazily, which makes it more efficient. Now, either proxy or data similarity views are then used to create a ranking of models in the end. The logical components of Shift are as follows. A user specifies a query, which is then parsed into a query tree. Now, if every part of this query tree or every subquery node in this tree can be evaluated and the results are known, then the list of models is returned to the user. Otherwise, tasks are defined and deployed by the task scheduler onto specific devices. In the execution layer, we have three different parts. One is an inference layer, one is a proxy layer, and one is a data similarity layer. So we optimize the first two in this work. Now, in order to understand what these layers do and what a task is, let us look at the task definitions. We have three different tasks. An inference task takes a model and the data reader and computes the last layer representation and embeddings and stores them again as data readers in the data reader view. A proxy task then takes two data readers. One is usually a training dataset and one is a test dataset in order to compute the accuracy or the proxy score for a downstream task. And the data similarity task computes a representation for a dataset for finding the closest dataset in task2wek. In order for Shift to be efficient, we also propose many optimizations in this work. First of all, as I said before, we only run costly evaluation when we need it. And this is especially important when we have multiple or nested queries, which we rerun the same thing over and over again. We also split big inference tasks into smaller jobs in order to fully utilize multiple GPUs. And one thing to notice here is that inference is embarrassingly parallel, whereas when we have proxy scores which rely on last layer representations, we need to be a little bit careful with dependencies. Then, if we require the top 1 or top k models, we can apply a technique called successive halving in order to not have to run inference on the full training dataset on all the models. And I'll go into this a little bit more in details. And finally, we also want to efficiently be able to support incremental execution. Let it be when we add or remove a model and rerun the same query, but also when we change or add data. And the techniques here we use are memoization. So we basically cache, and we don't need to rerun the same inference or even classification job twice, but we can reuse intermediate results for this. Successive halving is a technique coming from pure exploration non-stochastic bandit theory. So in that, we define a number of ARM pools, and an ARM pool is basically running a portion of the data set through a model. So we start basically with all models at the beginning, and after having run inference and getting the proxy score for a fraction of the data set, we eliminate the worst half of the models, and we only keep the better half, like the lower half here. We double the number of ARM pools, meaning that we double the number of data we show to the model to compute the proxy score, and repeat this process until we only have the number of models required in the end. Now, while this works really well, we need to be a little bit careful when adding data and re-executing the same query. So basically, if we would add the data at the end of this data set, models eliminated at the beginning of this process would never have a chance to even see the data. So what we do here, we define a second data set, which is this the data which needs to be added to the process. And we split this second data set into the same number of chunks as we have in data set 1. Now what we do is we build virtual chunks by combining the first chunk from the first data set and the first chunk from the second data set. And we only need to run inference on the second data set, so we can reuse the inference task or results from the first data set, but we have to recompute the proxy for the virtual chunk 1 and virtual chunk 1 and 2. Now let me show you some numbers. Apart from being able to run all this diverse set of queries, we also show that the optimization of shift are very helpful. So in this example, we use CIFAR on a set of 50 models, and the baseline of fine-tuning all models requires us to, on one GPU, requires 250 hours, whereas running the queries without optimization of shift is already 2 orders of magnitude faster, almost. And using the optimization of shift even enables a speed up of a factor 2. Now, before I conclude this talk, let me show to you a second use case of shift. The second use case, imagine you have a data set which might be noisy or have missing values, and we have a target accuracy. Now, the system called Snoopy, the idea of it is to estimate the accuracy of the data set. Now, if the target accuracy is within that estimate, then we're probably good to continue with the machine learning project. Otherwise, it is probably wiser to change the task or the data. You can find more information about shift and why this works and how this works and what are the edge cases one needs to consider in work we published this year at ICD. But the nice thing with shift is that EasyML Snoopy, or this system of Snoopy, basically only reduces to a very simple query for shift, which is we want to get the minimum 1 in n error over all possible transformations. And this is basically query 2, where we don't care about which model is returned, but we care about the cosine nearest neighbor accuracy, or the error, in order to compute the range of accuracy which is achievable on that data set. And using shift to run this query, we can nicely apply all optimizations and get a big speed up over the original system. And with that, I conclude my talk. Thank you very much.